So my talk follows on. It's in the theme of this session. I'm going to be, again, considering habitability for low-mass exoplanets around M-dwarfs. But it's really going to be focused more on the climate problems, and in particular for the Gliese A581 system. I'm going to be doing a case study of that. So you've heard lots about it already. I'm going to tell you some more. Just as a refresher, this is a red dwarf star. It's 20 light years away from the sun, so in astronomical terms, it's very, very close to us. And it's so fascinating to us, obviously, because of these low-mass super-Earth exoplanets that are in the process of being discovered around it. Where's the pointer on this thing? Oh, is this? Got it. So yeah, this is, I'm mentioning two of them here. This is Gliese 581c and 581d, both discovered by Stefan Udry's team in 2007. So this one has a minimum mass of around 5.4 Earth masses, and it's got a close-in orbit and hence a relatively high equilibrium temperature. 581d is a little bit bigger. It's further out, and hence its estimated equilibrium temperature is going to be much lower. And so I think it's nice to compare the orbits in the system with Earth's, with the solar system, so you can really get an idea of the context of it. This is a plot from Vogt et al., so I'm going to ask you to ignore some of the lines here. But if you just focus on C and D, you can see that compared to the solar system, this is Mercury's orbit here. This is an incredibly compact system. And the fact that these planets' equilibrium temperatures straddle those of Earth, it really tells you just how feeble the host star is. So the question, obviously, all of us are interested in is whether or not these planets could be habitable. And just to make clear once more here, I'm going to be talking about habitability in the context of whether or not they can support water cycles, whether or not they can have oceans. We know there's plenty of other issues that are significant for this, but this is what I'm focusing on here. And I'm showing you, yet again, the famous habitability zone plot. So originating from casting study in 1993, but then it was taken by Frank Salsisse in 2007 and applied directly to the Gliese 581 system. And so basically these planets both straddle they're both tantalizing close to the inner edge and outer edge of the system's habitability zone. With the sea planet, in fact, when it was first discovered, it was its equilibrium temperature led people to think that, you know, at 60 degrees Celsius, maybe this planet could have really quite nice conditions on it. But if you look at the climate modeling, in fact, if you imagine Gliese 581c with liquid water on its surface, an ocean, something like that, it's basically impossible to escape with any reasonable assumptions on the clouds in the atmosphere, the runaway greenhouse effect. So you pump more and more water vapor into the atmosphere, the whole system heats up, and before you know it, everything evaporates and the planet becomes completely inhospitable, like we expect happened to early Venus in the solar system. So 581c nowadays is looking like not such a good candidate for the first potentially habitable super-Earth. I'm going to move on to talk mostly about 581d in this talk, but I have to just mention another planet in the system before I do so. And this is the famous, or perhaps infamous, 581g, which was around 6 months ago, maybe a bit longer than that now. There was an announcement by Stephen Vogt and their team in the States that a new exoplanet had been discovered right in between 581c and 581d in the system, which obviously places it right in the habitability zone. And they estimated as well it had a lower minimum mass than either of these planets. And yeah, so that's it there. Oops. Yeah, so we theorists or exoplanet modelers don't like to waste much time, and so within a few months there was already theoretical studies coming out as to what the potential climate of this planet could be. There's a kind of fascinating paper by Ray Pierre Humbert that appeared in APJ Letters around the start of this year about what kind of climate state this planet could have. I'd like to talk about it more, but I'm not going to, because, as perhaps many of you know, there's in recent months been really severe doubts coming out as to the validity of this detection. So I know there's been unpublished criticisms by the Geneva team, but more recently there's also been two new analyses that have just been published, which are using Bayesian statistics, I think, to really put into doubt whether or not this planet even exists. So for the moment, 581g is also out of the picture. So kind of like parallel to when all this controversy was going on, our team was getting more and more interested in modeling 581D. Using the classical calculations, it's either just on or just inside the edge of the habitability zone, as I was saying. So that means there's really quite a lot of interesting issues about whether it could be, whether it could support liquid water or not. And we decided to take a closer look using our climate models. So we took the initial assumption, hypothesis I should say, I guess, that the planet had an atmosphere with some mix of carbon dioxide, water vapor, and nitrogen in its atmosphere. And you can sort of reasonably, well, you can plausibly justify this by the fact that in the solar system, all the terrestrial planets with atmospheres, their greenhouse effect is dominated by CO2 and water, but it is essentially just a guess, and I'll talk about other possibilities towards the end of the talk. So yeah, the model that we use, it takes high-resolution spectra and then converts them into a form where they can be processed easily, either in one-dimensional model or in a 3D model, and the radiative transfer. The idea being that we can essentially put in any kind of atmospheric composition we want to, and then simulate that and see what kind of climate we get. Having said that, the caveat of that is obviously that we always need good optical data in our model, and one of the things we worked on very hard in the beginning was to improve our calculations for dense CO2 atmospheres. In fact, what we found, we were also looking at stuff related to early Mars, but we found that the warming is slightly reduced from what we expected using previous models in these cases, so this was just another point. And so now moving on to atmospheric scenarios for Gliese 581D. You're looking at a case with a 40-bar CO2 atmosphere, and you're looking at the stellar radiation reaching the surface. And one of the first things you find as soon as you start looking at climate modeling in M-class systems is just really the dramatic effect that the stellar spectrum has on your results. So here what I've done is given a calculation with the same flux as you expect for 581D, but insulated by a sun-like star. And so we have a lot of radiation lost due to space, scattered back due to Rayleigh scattering, the phenomenon that makes the sky blue on Earth. This raises the planetary albedo and ultimately very much limits the amount of greenhouse warming you can get by adding more CO2 or other greenhouse gases. If we shift to an M-class spectra, it's obviously red-shifted, so you can see the Rayleigh scattering has a much, much smaller effect. There is decreased radiation reaching the surface in these bands due to the near-infrared absorption of CO2, but this tends to occur, a lot of this occurs either in the middle or lower atmosphere, so this can still contribute to warming the planet. And you really then see in the, if you look at, for given surface pressure, the surface temperature you get, the great difference between these two cases. If you have a sun-like star, then you never get anywhere near temperatures where you have liquid water. You, even for like 2 or 3 bars, eventually just the atmosphere starts to collapse on the surface, so forming dry ice rather like you get on Mars today. In the red dwarf case, you can keep adding CO2 and you keep warming, and when you get to around 10 or 20 bars, then you get above the point for liquid water. So that's pure carbon dioxide. Now if you add water to that, we know from extensive climate studies on Earth and other planets, the water vapor is a very potent greenhouse gas, so as you might expect, this reduces the total amount of CO2 you need in order to get habitable temperatures. If we add nitrogen, there's known on Earth that nitrogen has a very weak greenhouse effect due to the broadening of pressure lines, but this is counteracted by the Rayleigh scattering that I was just talking about. But as I was just saying, of course, in M-class systems, Rayleigh scattering is less important, so again, nitrogen can have a warming effect. And I just mentioned the paper from von Paris et al., because as far as I'm aware, they were the first study in the literature to point this out for M-class systems. So this is all looking pretty well and good. It seems like there are definitely climate scenarios where this planet might be habitable. But unfortunately, it's not the end of the story from the modeling side, because we really need to look at in 3D, whether these atmospheres would be stable. This really follows on from what René was talking about with the varying obliquities and so on of these planets. If you have, for example, a permanent night side, then you have a great worry that it's going to become so cold on that side that the atmosphere will collapse on the surface. Oh, and so to do this, we used the 3D version of our model, which is sort of related to Earth-like climate models. We advect clouds and temperature and so on in the atmosphere using fluid dynamical equations. I'm sort of running out of time already. Okay, so here's the 3D results, some of them anyway. This is tidally locked case, so as the moon is to the Earth, one side always facing. This is the 1-2 resonance, which René was just saying is perhaps the most probable rotation rate for Gliese 581d. And as you can see, when you have, as you might expect, when you have extreme resonance cases, you have large differences of temperature, but these tend to go down as you get to higher resonances. We systematically looked at this for a range of CO2 pressures. So now you're looking at the same kind of plots that I was showing before in 1D, except that the dots show you the annual mean temperature of the planet, whereas the error bars show you the maximum and minimum. And you can see that, in fact, in a lot of those cases we were looking at in 1D, the atmospheres globally are unstable. They collapse on the surface. Having said that, for both rocky and ocean planet cases, you get, when you get to the high enough pressures where you tend to get habitable conditions, the atmosphere is getting very efficient at transporting heat, so it always tends, in addition, it tends to be stable. So that is clearly showing our scenarios associated with this planet where it's potentially habitable. I'm going to skip through just talking about that. Essentially, CO2 is just one. These kind of CO2, N2, H2O atmospheres are one scenario for the planet, but there's absolutely other possibilities. For example, it's quite a large planet, so it could have kept some kind of hydrogen envelope. This may have interesting implications in terms of the chemistry in the upper atmosphere, but with most kind of hydrogen envelopes, it'd be far too hot at the surface to support liquid water or to have life. And on the other side, we know that XUV fluxes are very strong in M-class systems, so the atmosphere could have been removed entirely. Okay, I've really run out of time now. I'm going to skip this. Essentially, and we use them to distinguish the possible scenario, or to propose observational tests for distinguishing the possible scenarios. So the reds and blue curves are for our model, the outgoing fluxes. The grey curve is for a planet with no atmosphere. In the case with no atmosphere, you have large orbital flux variations. And if you have a CO2 signal, equilibrium chemistry in H2 atmospheres tells you that that should be more or less undetectable. So the upshot is, we think if we get a strong CO2 signal that doesn't vary very much, it's a pretty good indication of the kind of atmospheres I've been talking about. And I'll just leave the conclusions there and take questions.